Myself, Shaijil J, Department of Mechanical Engineering, Malabar Polytechnic College, Kottakkal. In this session, I am going to discuss the last year question paper of Material Science and Metrology. The course code is 3022. Part A, one more question. What is space lattice? It is a three-dimensional arrangement of imaginary lines connecting atoms is called space lattice. Second question, describe hardness. Hardness is the measure of the resistance to localized plastic deformation of the material. Another way, it is a property of the material to resist indentation or aberration. Third question, what is the principle behind liquid penetrant testing? The principle behind liquid penetrant testing is capillary rise. Fourth question, what is aided and unaided visual inspection? Unaided visual inspection means the inspection done by naked eye. Aided visual inspection means it is using some optical instruments, that is the inspection done by some optical instrument, that is called aided visual inspection. Fifth question, explain creep failure. The time-dependent deformation of a material under constant load at elevated temperature is called creep failure. That is, a creep failure takes place at elevated temperature by taking long time, or it is under a certain duration of time is required for changing or the dimension of deformation. That is called creep failure. Give another name of ductile fracture. Ductile fracture is also called cup and cone fracture. Seventh question, describe direct method of measurement. This is a method where value of the quantity to be measured is obtained directly without any calculation. Such a measurement is called a direct method of measurement. Name any two methods of angular measurements. Sine bar, bevel protractor, clinometer, etc. are the equipment used for angular measurements. What is surface roughness? Process marks or witness marks produced by the action of cutting tool, that is called the surface roughness. Part B, 3-mark questions. First question, explain HCP structure with the figure. HCP means hexagonal closed packed structure. HCP structure consists of 12 corner atoms, 2 atoms at end faces, and 3 atoms entirely inside the unit cell. The net effect of 6 complete atoms in the unit cell, it follows AB pattern of arrangement. Here you can see that each corner consists of 1 atom. You can see there are 6 corners at the top and 6 corners at the bottom. So total 12 atoms at the corners and 3 atoms at the center of this hexagonal prism, and 2 end face atoms you can see here. So net effect is 6 complete atom in a HCP structure. Second question, give the composition of pig iron and how is it produced? Pig iron is produced in blast furnace. Pig iron is produced by the smelting of iron ore with high carbon fuel and reductant such as coke, usually with limestone. It is the first product in the process of converting iron ore into useful metal. Pig iron is is the raw material for all iron and steel products. The composition of the pig iron is, it consists of 90 to 95% of iron, 3 to 4.5% of carbon. That is very important. Sometimes it is asking what is the carbon percentage in pig iron. That is 3 to 4.5 percentage. Silicon is approximately 0.5 to 4 percentage. Phosphorus 0.025 to 2.5 percentage. Third question, explain ductile fracture. In some materials, fracture occurs after some amount of plastic deformation. Plastic deformation occurs prior to and during the propagation of the crack. Such materials are said to be ductile and the fracture is termed as ductile fracture. Ductile fracture is always preceded by the localized deformation called necking, and it is also called cup and cone failure. That is important phenomena is there will be a plastic deformation in the case of ductile material, and there will be, you can see in this figure, you can see initially there is a reduction in the cross-section area, that is called necking. Then some cavities are formed in the neck region. Then the cavities are linked up. Then there is a crack and propagating, and this failure, this is a cup and cone shape failure. Fourth question, draw the graph describing tensile test on ductile material. This is a stress strain graph of the mild steel specimen. You can see that different regions or points marked on this graph. Here initially the y-axis it is taking stress, and on the x-axis you are taking strain. Up to a certain limit it is linear and it is both stress and strain are proportional. That region is called proportionality limit. You can see this is a proportionality limit. Here up to some extent it is a proportionality limit. Up to that region stress and strain are directly proportional. After that it is a linear. Stress and strain are directly proportional. It is linear. After that it is non-linear. Up to a certain limit it is called elastic limit. If you remove the stress or unloading it, it will be regains back to its original point. So it is very close to proportionality limit. Elastic limit and the proportionality limit are very close. And then if you increase further, the stress is increased. You can see it is at some point there will be yielding will be take place. That means the strain will be happening, but there is no increase in the stress value. Here there is a particular stress value. There is no further increase in stress, but even though there will be strain is happening, that point is called a yield point. The corresponding strength is called yield strength. After yielding, there will be strain hardening region. That is, you can see this is called strain hardening. Again, the stress is increasing. At a certain point, that is called ultimate strength point, there is a change in the cross section is starting. That is, necking will be happen. Further again, the stress is reducing. That is, this leads to the fracture. The end point is fracturing of the material. That is the fracture stress. That strength stress value is called fracture stress. So this is a proportional limit in this region. If you find out the slope, you can find out the Young's modulus of the material. That is, slope is equal to stress by strain. Fifth question, give the equation for Vickers hardness number and explain the terms involved. Vickers hardness number HV, that is equal to 1.854 into F divided by D1 plus D2 by 2 whole square. The terms here, it is in the force, F is in kilogram force. That is, in the case of Vickers hardness test, we are using is the diamond pyramid we are using. You can see the cross section of the diamond pyramid. This is a specimen, sample specimen. And after indentation, we will get this is a top view of the indentation. And D1 and D2 are the parameters of the diagonals of indentation in the top view. That is the values of D1 and D2. The mean value, that is D1 plus D2 by 2, that is the mean value. We can find out the hardness value using Vickers hardness. In this case, you have to remember diamond pyramid indenture is using and the angle of the indenture is 136 degree. Sixth question, briefly explain liquid penetrant test. Liquid penetrant inspection or test is one of the oldest and most widely used non-destructive testing methods. It is also called as dye penetrant test or dye penetrant inspection. Liquid penetrant test is used to detect surface defects such as cracks, seams, porosity, folds, etc. Generally, it is used to find out the cracks in the surface of the material. It can be applied to ferrous and non-ferrous materials. The penetrants are mixtures of organic solvent which are characterized by their ability to wet materials and spread rapidly. The principle behind liquid penetrant test is capillary rise. We are using developer. Developer is a good absorbent material capable of drawing traces of trapped penetrant from the discontinuities and back into its surface. Here you can see there is a crack in the material. It is filled with some dirt or grease, something will be there as an ordinary component or a material. The first step is to clean and dry the object or the component. So we are ideally cleaned the material, then we are applying the penetrant. Penetrant is applied to the surface and if there is a crack, it will be entering into the crack. And after applying the penetrant, after some time we will remove the penetrant from the top. Where we are checking the surface. So we are removing it. Intermediate cleaning we have done. Then we are applying the developer over the surface of the penetrant, over the surface of the component. So what happened is that this developer will develop or some color or penetrant from the crack. So you can see the due to capillary action, the penetrant comes out here in this region when we applied the developer. So we can identify that where the indication comes out, that region there is some crack is occurred that we can find out. That is called a liquid penetrant test. That is, we can evaluate the indications of the by its color of the liquid. Seventh question. Name the stages involved in measurement system. The measurement system involved 4 stages. First is called a sensing stage. We are sensing the data or whatever maybe you have to measure. Signal conditioning. It will be producing some signal. That signal conditioning stage is the next one. Then the data presentation stage. Then feedback control stage. That are the 4 stages involved in the measuring or measurement system. Describe spring balance. The spring balance is a device which is used to measure the force directly with the help of coil spring deflection. The working principle of spring balance is Hooke's law. The fixed end is attached to catch hook for holding it and free end is connected to the load to be measured or load hook. It is connected to the component we have to measure the weight of the component that will be hooked to the load hook. The displacement at free end due to the applied force is shown by pointer moving on a scale. Here the deflection is linear function of force and can be used to measure the force directly. By the equation F is equal to K into delta. K is the stiffness of the material of the spring and F is the force applied. For a spring, K value is a constant. So we can find out the force by using this equation also from the deflection. Ninth question. Describe the classification of autocollimator. An autocollimator is an optical instrument for non-contact measurement of small angles with a very high sensitivity. It is an angle comparator based on the principle of reflection of light. Autocollimators classified into three types. First one, visual or conventional autocollimator. Second is digital autocollimator. Third is laser autocollimator. 10th question. Sketch and mark the parts of clinometer. Clinometer is an instrument used to measure angles or slope of elevation or depression. The different parts of the clinometer are: there is eyepiece is there is a fine adjustment nut is there, split level is there, one base is there, a lock nut is there, an angle scale we can see to measure the different angles. Next is part C, 7 mark questions. Give the composition of stainless steel. Also mention its properties and applications. The composition of stainless steel is it consists of different materials like iron, chromium, nickel, manganese, and some other elements are there. Nearly 75% is iron. Chromium, about 15% chromium is present. Nickel 9 to 9.5%, manganese 0.5%, and small amount of other elements are also present. Stainless steel is most important property is corrosion resistance due to stable layer of chromium oxide. Here you can see we are adding nearly 15%, that means about 12% of chromium that will be creating this stable layer of chromium oxide which create corrosion resistant property. That is why this type of steel is called as stainless steel. The major applications of stainless steel are food and catering operations, chemical and pharmaceutical industries, medical equipment manufacturing, architecture and construction, home appliances, automotive manufacturing, energy and other and industry oriented. Properties of the stainless steel materials. The most important property is the corrosion resistance due to stable layer of chromium oxide. Other important properties are it has high yield strength, tensile strength, high ductility, hardness and toughness. Creep resistant and fatigue resistance are also the properties of the stainless steel material. Next question. What are isomorphous eutectic and eutectoid systems? Give examples. Isomorphous system. In this system, the two components are completely soluble in liquid and solid state in all proportion, then it is called an isomorphous system. For example, copper nickel system is an isomorphous system. Silver copper system is also an isomorphous system. Here you can see that we are taking nickel and copper. Here different percentage of nickel you can see here 20% of nickel and 80% of copper, 40% of nickel and 60% of copper, and nickel is increasing in the x-axis. On the opposite direction the copper is increasing. So in any proportion you can see it is completely soluble to a single phase. It is called isomorphous system. So liquidous line, above liquidous line it is in the liquid state, below the solidus line it is completely in the solid form, but it is in the single phase. So we can say all proportion it is completely soluble, that is why it is called the isomorphous system. Next is eutectic system. A eutectic system is a homogeneous mixture of two or more substances that melts or solidifies at a single sharp temperature lower than the melting point of any of its individual components. Eutectic means easy to melt. That means it will give the eutectic system, eutectic point will give the lowest temperature to be melted. This unique behavior occurs at a specific ratio of components called eutectic composition. The eutectic reaction will be occurring at the particular composition that is called eutectic composition and at a specific temperature called eutectic temperature. For example, lead tin system, silver copper system are examples for eutectic system. In the eutectic system, from the liquid phase, the liquid solidifies on cooling and this arrow indicating heating. Liquid on cooling, it becomes solid 1 plus solid 2 at two different phases. For example, liquid metal on cooling will get a mixture of austenite plus cementate. That is simply called lidaborate. So, lidaborate formation in the case of iron-carbon diagram is a eutectic system. Next is eutectode system. A eutectode system is a transformation where a single solid phase transforms into two different solid phases at a specific temperature and composition. The eutectode system, a solid phase on cooling transform into two different solid phases. This occurs in the iron-carbon system where austenite, a solid phase, transform into a mixture of ferrite and cementate. That means two other solid phases called perlite at the eutectode point of 723 degrees Celsius. That means a solid on cooling gives two other solids phases, solid 2 and solid 3. In the iron-carbon diagram, on eutectode point, the austenite transform into ferrite and cementate. That is called a perlite. That is, a perlite formation is a eutectode system. Here you can see the eutectode transformation. This is austenite on cooling, it become alpha plus Fe3C, that is ferrite plus cementite. Here it is become ferrite plus cementite. Ferrite alpha is indicating the ferrite and here it is Fe3C. So this together two phase, this is called microstructure is called perlite. Draw the iron-carbon diagram. The iron-carbon diagram is also called iron-carbide diagram. It is also called iron-carbon phase diagram, iron-carbon equilibrium diagram, or iron-carbon constitution diagram. The same manner it is also called iron-carbide phase diagram, iron-carbide equilibrium diagram, and iron-carbide constitution diagram. Because it indicates this diagram, it is first called phase diagram because we can see the different phase changes occurring in the cooling process at a different composition. It is called equilibrium diagram because it is cooling is at a slow rate, so it is passing through the equilibrium states. That is why it is called equilibrium diagram. It is also called constituent diagram because we are taking different binary solid solution or binary system. So two different constituents of different compositions are taken. That is why it is called a constitution diagram. So any way it is be asking different name, the same question can be asked in the 6 different names. So we remember the different names. This phase diagram describes the iron-carbon system of alloys containing up to 6.67% of carbon. This crosses the phase composition and their transformation occurring with alloys during their cooling or heating. Carbon content at 6.67% correspond to the fixed composition of the iron carbide. That means at 6.67% of carbon it become completely iron carbide. That is why it is also called iron carbide phase diagram. This is the iron carbon phase diagram. We have to remember in this picture, in this diagram, we have to remember different percentage of carbon at different points, different invariant reactions, different temperatures, what are the structural changes occurring when it is passes through different phases. First of all, the temperature, you can see the extreme Y line, side of the Y, you can see this is the alpha Fahrenheit. Next is called gamma austenite. Here you can see the delta. That is here the melting point of the pure iron, that is 1538 or 39 degrees Celsius. That you can see here. Above that it is completely in the liquid state. We are taking carbon from nearly 0 to 6.61%. Here in this region it becomes completely iron carbide. We are not going for 100% carbon. At 6.7% it becomes completely iron carbide. So further more than 6.7 is not required. In this diagram you can see it 2.4, 2.14, that is 0 to 2.14 is a region for steel, and 2.14 to 6.67 is theoretically the range of cast iron. We can see the different reactions here. This is a eutectic point, the liquid on cooling. This you can see the lowest melting point here. This point is 4.30 composition of carbon. This point is called eutectic point. Here at 0.76% of carbon at 723 degrees Celsius. This is a eutectoid point. And here one more point is there. That is, it's called peritectic point. That is, from this region you can see delta plus liquid region. It is after peritectic reaction it becomes austenite, a single solid. From the solid liquid phase to a single solid. That is called a peritectic reaction. So you have to identify these different regions on this diagram. This is here alpha, this is austenite, and this is delta. So if you know the two regions, we can find out the intermediate region. This is alpha and this is liquid. So this becomes alpha plus liquid region. This is alpha and this is austenite. So this become delta and this is austenite. So this become delta plus austenite. Here it is austenite and here it is liquid. So it become austenite gamma plus liquid. Here it is alpha and here it is austenite. So this become alpha plus gamma or alpha plus austenite. Here in the eutectic reaction, you can see the eutectic reaction. Here this is a eutectic reaction. It will produce a lidaborate, that is austenite plus Fe3C, that is a lidaborate. Here the eutectoid transformation. Here we will get perlite. You can see here the point here perlite is forming, that is ferrite plus cementate. Ferrite means alpha plus Fe3C, that is the perlite. Here you can see the different transformation to different region. Here it is austenite, then it become, when it is reaches this region, that is alpha plus austenite, you can see some ferrite is forming here. Again it is gradually growing, and finally it become, when it is reaches in this region, you can see it consists of perlite, and also it is trieutectoid ferrite you can see, and iron carbide and eutectoid ferrite you can see. So this is the iron carbon diagram. So we must know the different temperature, different composition, and different phases. What is transformation occurring in particularly in the austenite to lower temperature region. Next question, briefly describe BCC, FCC and SC lattices. BCC means body-centered cubic crystal. FCC means face-centered cubic crystal. SC is simple cubic crystal lattices. That is the full form of the different names. Here first one is a simple cubic. Simple cubic means the lattice parameters A, B, C are equal. You can see A, B, C. All cubic cube, it is all parameters are equal, and angle between these parameters are also 90 degree. If it is a simple cubic, that means only the corner atoms are present. So you can see total 8 corners are there, 8 corner atoms are there in the simple cubic. There is no other atom. So the meaning is that 1 by 8 of this corner atom is shared only by this unit cell. In the next case, body-centered unit cell, there is again you can see 8 corner atoms, 4 at the bottom, 4 at the top. And there is a, if you draw the body diagonal, you can find out a body diagonal atom also there. At the center of the body, one more atom is there. In the case of face-centered cubic unit cell, you can see again 8 corner atoms, 4 at the top and 4 at the bottom. And there are 6 faces for the cube, and each face center there will be, you can see the atoms. 1, 2, 3, 4, 5, 6 atoms will be there. That means in the simple cubic, the total net effect of atom is only 1. If it is a body-centered atom, net effect is 2. And if it is a face-centered, total number of atom present, that is the net effect of atom is only 4. Simple cubic, cubical crystal in which 8 corner atoms are present. FCC face-centered cubic, 8 corner atoms and 6 face atoms at the center of each faces. Body-centered, there is again 8 corner atoms and 1 atom at the center of the crystal or of the cube. Next question, how pulse echo system works? Give a neat sketch. It is also called ultrasonic inspection. This is a inspection method, pulse echo system. Another name is ultrasonic inspection. It is employed to detect and locate defects such as shrinkage cavities, internal burst, or cracks, porosity, and large non-metallic inclusions that are present inside the material, that we can find out using this pulse echo sound waves. Ultrasonic vibrations can be used to locate defect in ferrous and non-ferrous metallic object as well as in plastic and ceramics. Ultrasonic inspection for detection makes use of acoustic waves or sound waves with the frequencies in the range between 20 kHz to 20 MHz, which can be transmitted through solid and get reflected by the subsurface defects. That means this is mainly used to identify the subsurface defects. This is something, the defect is just below of the surfaces. The ultrasonic waves are usually, and we can also find out the depth where the defects are present, that we can also find out. It is not used for finding the surface defects. Ultrasonic waves are usually generated by the piezoelectric effect, which converts electrical energy into mechanical energy. So using a piezoelectric crystal, the electrical energy is converting into mechanical energy. So it will be producing some vibration. That waves is passing through the material. A quartz crystal is used for this purpose. Wave is sent from the transmitter probe. For providing this sound wave, we are using a transmitter probe, which consists of this quartz crystal piezoelectric material. They strike the upper surface of the casting and make a sharp peak at the left-hand side of the CRO screen. When it is strike at the top surface, impingement or small vibration, it will be shows a sharp peak at the CRO means cathode ray oscilloscope screen. On the left side of the CRO, we can see a sharp peak uh, variations. If the casting is defect free, if there is no defect, this wave will be strike at the bottom of the surface of the casting. Surface of the casting get reflected and indicated by the peak towards the right hand side of the CRO screen. That means if the material having no defect, there will be two peak signals you can see in the left side and right side. Left side is the starting point and right side is the bottom point of the surface. So we will get the, if there is no defect, only two peak uh, variations or waves we can see in the cathode ray oscilloscope. If there exists any defect in between top and bottom of the casting, after the beam striking the defect gets reflected. If there is a defect is present during the movement of these waves, so it will be get reflected from that defect. Reaches the receiver probe and indicate a peak on the CRO screen before peak given by the wave striking the far end of the casting and returning. So you can see here is a defect-free material. You can see the material. We are moving the probe from here to here. So here you can see the defect in the material. Here no defect in the material. So this is a probe which is sending the vibrational waves downwards or acoustic waves downwards. So it is gradually moving, the waves is producing downwards, and also we are moving the probe on the surface. This is a CRO screen. We can see the peak and here in this different waves you can see here. If it is a defect-free material, the starting you can see a left peak wave here you can see, and there is not, it is touching the bottom and returning. So there is a peak at the right side. So there is no defect in this region, this depth, there is no defect. In this case, there is a defect is there. So it is starting, you can see there is no, at this point there is a peak on the left side, but due to this defect, it will be reflected back. So there is a peak in between the bottom and the top faces. We can see this, some waves are showing. That means there is some defect is present. That we can also calculate depth where the defect is present. Also, we can identify from the CRO cathode ray oscilloscope. Next question: explain case hardening. Case hardening or surface hardening is a process of hardening the surface of a metal object while allowing the metal deeper underneath to remain the same, thus forming a thin layer of harder material or metal at the surface and a tough core. In the case of case hardening, some material requires certain properties or compound requires some properties to resistance to abrasion, indentation, etc. when it is working. For example, here it is working for many hours. So the surface to be hard to resist the wear and tear. So we are doing the surface hardening. That means the outer surface is hard and inner core is soft or tough to take the shock. So such a kind of operation is called case hardening. Case hardening is achieved by adding carbon, nitrogen, or both. That means when carbon is adding to some surface, it form carbates. Nitrogen adding nitrate, so it will become harder when it is adding the atoms of carbon and nitrogen diffusing into the surface metal part in order to provide hardened surface case. The process used to create the hardened cases are carburizing, nitriding, cyaniding, and carbonitriding. In the case of carburizing, we are adding carbon to the surface of the material. In the case of nitriding, you are adding nitrate means nitrogen. We are using nitrogen to make it hard. Cyaniding, it is using both carbon and nitrogen. For also carbonating, we are also using carbon and nitrogen. For adding carbon, in the case of carbonizing, we are using the materials like charcoal, coke, coal, carbon monoxide gas, etc. We can do with the help of solid material. We can use it with the help of liquid materials. Also with some gas, we can do the carbonizing operation. Nitriding, for nitriding, we are using ammonia gas. For cyaniding, we are using sodium cyanide, NaCN. Carbonitriding, carbonizing gas, and ammonia is using. Carbonizing is a method of introducing carbon into the solid iron-based alloys such as low-carbon steel in order to produce hard case. Carbonizing is also called cementation. Carbonizing increases the carbon content of the steel surface. Here, low-carbon steel is heated at 870 to 925 degrees Celsius in contact with the gaseous, solid or liquid carbon containing substances for several hours. The high carbon steel surface is hardened by quenching. Carbonizing causes negligible change in dimension. The important peculiarity is carbonizing causes negligible change in dimension. There is no change in the dimension. If you are heating the material and doing some other process to increase the hardness, the dimensional change may be occur. But in this case, it is by diffusion. There is no dimensional change or very, very negligible. For example, it is used in the case of gear manufacturing, gears, camshaft, bearings. We are using carburizing. Here you can see all the processes like carburizing, nitriding, cyaniding, and carbonating are same. The manner of doing the work process. That is, there is a container. You can see this is a container which is insulated container. We are applying heat to the component is placed inside this container. Surrounding this component, component is at the center. Surrounding this component, what kind of process we are doing? That is, for example, if it is a nitriding, we are to nitrogenous atmosphere to be created here, like ammonia gas or sodium cyanide, etc. Here it is carbon monoxide, that is, we are adding carbon to this component. So here the carbon dissociate and the carbon will be entering into the surface of the material at this high temperature. So if you are increasing the period of time, the depth of hardening is also increasing to some particular limits. So it depends upon the temperature and the time we are doing this process. That is rate of diffusion will take place. The carbon will be entering into the surface of this material. That is take place in the atomic level. If you are providing ammonia, the nitrogen will be entering. That is, nitrogen will happen. The process remains same. For example, if you want to do a cyaniding process, we are using sodium cyanide is using. Like thus we can increase the hardness, surface hardness of the material. So here you can see the product. For example, here the product is a gear. You can see the surface of the gear. You can see the teeth is hardened, the surface, but the core is soft or tough. Here the shaft, the surface is hardened, the case hardened, but the soft, the core is remain soft and tough. Next question, describe the terms hysteresis, calibration, threshold, and range. Hysteresis is the difference between the indications of a measuring instrument when the same value of the measured quantity is reached by increasing or decreasing that quantity. Hysteresis is a phenomenon under which the measuring instrument shows different output effects during loading and unloading. Calibration, the process of comparison of a device with unknown accuracy to a device with a known accurate standard to eliminate any variations in the device being checked is called calibration. Threshold, when the input of instrument is increased gradually from zero, there will be some minimum value below which no output change can be detected. This minimum value defines the threshold of the instrument. In other words, the minimum value of input below which no output value is achieved is known as threshold. Range. Range means range of an instrument describes the lowest and highest values that can be measured using that particular instrument. For example, we are using a ordinary scale. We can lowest dimension we can measure is maybe 1 mm. So the largest highest value that may be 15 mm if it is a 15 mm scale. So that range that is indicating the lowest and highest values describe the range of measurements. Next question, explain the process involved in measurement. This is a generalized measurement system is a set of elements in which the measurement process is carried on by the system. The elements of the measurement system are, one is some input variables are there. It is sensor must be sensing these input variables. That is called a primary sensing element. Then there is a variable conversion element. Then it is where there is a variable manipulating element. Then signal transmission. Then data processing element, presentation element, and then to the observer. These entire things is called the generalized measurement system. Next question, describe classification of errors in measurements. The error in measurement is the difference between the measured value and the true value of the measured dimension. The error in measurement is equal to measured value minus true value. Errors in measurement can be broadly classified as systematic and random errors. Systematic error. Systematic errors are also known as controllable errors. They are consistent and similar form. These errors tend to shift all measurements in a systematic way. So when a number of measurements are taken, the mean value constantly varies in a predictable way. These errors can be determined and controlled. Systematic errors result from improper conditions or procedures that are consistent in action. Next, random errors. Random errors are non-consistent. These errors are those which are accidental, whose magnitude and sign cannot be predicted from the knowledge of measuring system and conditions of measurement. These occur randomly and specific causes of these errors cannot be determined. Few of the several causes of random errors are small variations in the position of setting, standard and workpiece, operator's error in scale reading, fluctuations in friction of measuring instrument, sight displacement of lever joints, that is a slight displacement of lever joints of measuring instruments. These are the few causes of the random errors. Explain mechanical strain gauge. A strain gauge is a resistor used to measure strain on an object. When an external force, that is the main application of the strain gauge, the main purpose of strain gauge is to measure the strain. When an external Force is applied on an object due to which there is a deformation occurs in the shape of the object and it is measured by the strain gauge. When an object deforms within the limit of elasticity, there is a change in resistance end to end. That is, we are using the resistance of the material to find out the strain of the material. The strain gauge is sensitive to that small change occurring in the geometry of an object. By measuring the change in the resistance of an object, the amount of induced stress can be calculated. Strain gauge has a long, thin metallic strip arranged in a zigzag pattern on a non-conducting material called the carrier, so that it can be enlarged the small amount of stress in the group of parallel lines and could be measured with high accuracy. Here you can see the figure of the sketch of the strain gauge. You can see the strain gauge, the wires are in a zigzag pattern on a non-conducting surface. It is fixed over a non-conducting surface. The strain gauge has a long, thin metallic strip arranged in a zigzag pattern on a non-conducting material called carrier. This is a carrier, and this is a thin metallic strip which is fixed over this carrier, and it is connected to an electric wires, so that it can be enlarged a small amount of stress when we are applying the force on this block. So it will be, there is slight changes will be occurring on this coil. So it will maybe increase in length or decreasing length, like that some changes will be occurring. So whenever this linear diameter is changing to this wire, so resistance will be also changing. So with respect to the resistance, by calculating the resistance from these leads, we can find out what is the strain occurring on the material. That is why the strain gauge is used to measure the strain. And see the strain applying force, it will be undergo some strain. Next one, demonstrate the working of Vernier depth gauge with the help of a diagram. This is a schematic diagram of a Vernier depth gauge. You can see here different parts are there. Is a main scale is there. There is a fine adjustment screw is there. There's a locking screw is there for locking this the position locking. Vernier scale is there. A movable head is there. One base is there. This last the bottom portion you can see the workpiece or a component where you have to measure the depth of a hole or depth of some particular point. You can find out in the component that you can measure. Here this is the working principle is same as that of vernier caliper or a vernier height gauge, but the moving things are different. In the case of vernier caliper, we are moving the main scale is fixed and we are changing the vernier scale. Similar manner in the vernier height gauge also. But in the case of vernier depth gauge, we are moving the main scale, but the vernier scale is fixed. Vernier depth gauge is used to measure the depth of the hole, slot, and the distances from the plane surfaces to the projection, used for precise measurements. Unlike a vernier height gauge, the vernier depth gauge does not have a heavy base. The main scale can slide through the base of the gauge body. Vernier depth gauge is made in such a way that the beam is perpendicular to the base in both directions. This differs from the vernier caliper and vernier height gauge in that the vernier slide assembly remains fixed while the main scale is moved to obtain the reading. That's the difference between vernier height gauge and the vernier depth gauge. That is, in this depth gauge, the main scale is sliding, But in the case of a height gauge, the Vernier scale is 5. What is a mechanical optical comparator? Explain. This is also called a Cook's comparator. The other name of mechanical optical comparator is Cook's comparator. As the name of the comparator itself suggests, this has a mechanical part and an optical part. Cook's comparator has a mechanical part and optical part. That is why it is called a mechanical optical comparator. Small displacement of a measuring plunger are initially amplified by a lever mechanism toward about a point. That is why it is a mechanical. That is a mechanical system. The mechanical system cause a plane reflector to tilt about its axis. So you can see a reflector is there. So it will be reflecting some light waves. That is, it is optical. This is followed by a simple optical system wherein a pointed image is projected onto a screen to facilitate direct reading on a scale. Here you can see the figure. The plunger, here you can see the plunger is there. Here is a plunger is there when it is moving over the surface or some what is common to be measured, it will be to be tested. So the plunger is, there is a pivot is there on this lever where the plunger is attached. So the plunger can move up and down. So due to this pivot, this and the plunger here moves up, this can be moved down. So the mirror is connected to by a link. So mirror is also pivoted here. You can see. So when this Z goes down, that means the mirror is also changing its position. It is also pivoted here, so it can change forward or backward because by the movement, based upon the movement of the plunger. Plunger is spring loaded. So from the light, so here a light source is this pass through condenser lenses and a projection lens strike on the mirror and it will be forming an image here on this scale. So due to the movement of plunger, it can be give a positive or negative variations on this scale. That is working of the mechanical optical comparator. Here the plunger is a spring loaded such that it is based on biased to exert a downward force on the work part. You can see it can always pushing downwards the spring loader. This bias enables both positive and negative readings. So when it is released, it can move upward. Otherwise, it is forced downwards. Depending on the on whether the plunger is moving up or down. Based upon that, we can get different readings from this. We can take the readings. It is positive or negative on this scale. Okay, thank you.